In this video we want to look at computational methods or numerical methods of solving an otherwise linear circuit that contains a single nonlinear element x. Alright, and for our example here we're going to use an element that has a VI relationship, that is V equal to K times I cubed. So that's the equation we're going to be using. Now in the previous lecture we had introduced the load line concept, and we're going to leverage off of that. And the solution the static solution to this circuit is where the load line of our Thevenin circuit, that's the voltage source and this resistor, intersects with the VI characteristic of our nonlinear element. So right here. And in this lecture we're going to look specifically at how can we solve this numerically, typically with the aid of a computer. So what we have is we're going to have a load line equation, and that will be a terminal voltage. If I simply have my Thevenin source, if you will, Vs, Rs, current IT, and a voltage Vt, we can write it as Vt equals Vs minus Rs times It. That's the load line equation. Now we have our nonlinear device equation, right? And all that is Vx is equal to some function of Ix. Right? So the solution will be Vt as a function of Ix will be equal to Vx function of Ix, which is equal to this f of Ix. Okay, and then we will solve for Vx, for Ix. Okay. Now, there's an alternate form of this. You could also rewrite this as current expressed in terms of voltage. And what would that be? That would be terminal voltage minus, source voltage Vs minus terminal voltage over Rs is equal to It. And then we could write over on the right side, perhaps we have Ix is a function of, say, g of Vx. Okay? And in this case the solution will be It function of Vx. Okay, I guess let me rewrite this right here. It here is a function of Vt. Okay, so It function of Vx will be equal to Ix function of Vx, and we'll solve for Vx. Okay, so it depends on the form of the nonlinear device. So for instance, what if we have a diode? All right, consider a diode. A diode, let's assume it was an ideal diode, and means it follows the Shockley equation. So the Shockley equation says that the current of the diode is equal to Is, some constant, times e to the diode voltage over a product of constants here, n times Vt minus 1. Okay. Now in this form, if you were going to try to use the first form of our nonlinear equation setup, we would have a problem, because we need to express in this case Vd as a function of Id. Okay, and if you look at this equation here, that's going to be tough to do. So in this case you want to use the second form, right? Which the way we'd set it up is we'd say Vs minus Vt over Rs is equal to the diode current. Let me actually replace Vt, right, the terminal voltage, I'll replace that with Vd. Okay, and then this is equal to Is e to the Vd over nVt minus 1. And here Is and Vt are constants. Okay, so we can just think of them as numbers. And this is your nonlinear equation. Okay, so take your tool of choice and solve for Vd. Now sometimes you can manipulate the nonlinear equation that for your device and get it into a form that allows you flexibility to use either of the equation, the nonlinear equation setups there that I just described. So for instance, this curve looks like this. If I plot ID versus VD, okay, it's an exponential curve, and when it's negative, this thing basically goes down to if you think of when VD is negative, this exponential term here is going to go to 0, and you're going to be left with ID is equal to minus IS. Alright. Well, typically IS is very, very small, and if you're looking at using this diode when it's conducting, which usually we're talking about using the diode when it's conducting, say we're using it in the milliamp range, that IS may be on the order of 10 to the minus 9, 10 to the minus 12, something very small. And so here we're looking at currents, maybe in this range of 10 to the minus 3 current. So for that reason we can approximate ID as Is equal to e to the Vd over nVt when diode is conducting. In other words, this is when Vd is greater than 0, basically first quadrant. Okay, so in that case, we could actually manipulate this. We could take the log of both sides. Actually, what we would do first is we could do ID over Is is equal to e to the Vd over nVt, and then we could take the log of both sides. When you take the log of an exponential, you're going to get just the exponent back. So now we can write Vd is equal to nVt log ID over Is. And this is essentially some function, right? Some function of ID. And so now that we can write the diode voltage in terms of diode current, we could go back and set up the problem according to this first equation configuration here, where we're expressing the voltage V, the load line voltage, setting that equal to the nonlinear device voltage as a function of I. But we could not do that with the original diode equation with the -1. We had to justify getting rid of that. But even if you couldn't have, you can use this second form right here, where you're actually going to be solving for Vx and not for Ix. Okay, so that's the basic setup. Okay, and now we can use several tools to solve this. So let's okay, some handy tools. For solving nonlinear equation. Okay. So one, we could look at Excel, because everybody seems to know Excel, so we'll look at that. We'll look at MathCad. We'll look at MATLAB. And then we'll look at using SPICE circuit simulation. Okay, so first let's click over to Excel. And I have a spreadsheet set up here. Come on. Okay. Alright, so here's how you do this. We're going to use what's called goal seek, the goal seek capability, and personally I don't really like this. It's you got to click through menus to get the thing to solve every time you change values. There are other ways to do it in Excel, but this is the most straightforward and the only one that I'm going to share at this point. So I've parameterized my equation. Here's just the text for it so we know what we're doing. I'm doing KVL around this loop. Okay, so we're doing minus V theta, or Vs, plus I times R theta, that's this term here, plus K times Ix cubed, that's the relationship that we're, the type of device that we have. Alright, and I've defined my Thevenin voltage, Thevenin resistance, and K right here. And then what I have in this cell here is actually the evaluation of that equation. Alright, and I've used name ranges, so you notice it actually reads like the KVL equation. And the V Thevenin's here, R Thev, K. And then I've added a cell here, Ix, with a number in it. So let me actually change this for the moment. And I'm going to go ahead and put 3 in there, for instance. And if I put some current in here, this current is the Ix that the KVL equation uses. So clearly if I put 3 amps, KVL does not add to 0. So what Excel needs to do is to iterate on this value of Ix, trying to get this cell here to equal 0. So here's how you do it. You go to the Data tab, and then let's see, formulas. Yeah, Data tab. Maybe I can't see it because oh, here it is right here. Goal seek. It's miniature because I haven't expanded my Excel window. So you click on goal seek. That brings up this cell right here, this pop-up. So you want the cell that you want to set is it's already picked this one right here, and you want to set that to a value of 0, right? We want KVL to be equal to 0, and you want to accomplish that by changing the cell over here that's Ix. Okay, and now we just simply hit OK, and it iterates, and it finds a value of Ix equal to 0.835, and that gets you to a pretty small value. Now what I don't like about this is if I change these values here, I have to go through and bring up that little menu again. But nevertheless, that is a method you can use, Excel. Okay, now let me show you let me show you MathCad. Is that the second one we're going to look at? Yeah, MathCad. So in MathCad, I've defined my variables R Thevenin, V Thevenin, and then I've defined what the Thevenin or load Thevenin terminal voltage would be as a function of IT, right? Just V Thev minus R Thev times IT. And then here's the constant for my nonlinear device, and here's Vx of the nonlinear device as a function of its current. It's just Kx times the cube of the current. I've plotted both of them here just so we can get a visual. And just looking at this, we expect the solution should be 1 amp and 5 volts. So let's see if we get that. Here's how you set it up in MathCad. So you define a variable that is going to be hold the value of the current, in this case, that we're going to be solving for. You give it an initial condition, and then it's important that you type in this statement given. Okay, and then it's important, MathCad, that's a keyword for MathCad. After that, you define what you're giving MathCad to actually solve. And what we're giving it is we're saying we want the terminal voltage from the load line as a function of IQ to be equal to the nonlinear voltage Vx as a function of IQ. And then we call the function find, and we pass it the parameter IQ. So it's going to iterate on IQ, making this equality here 0, or satisfying this equality. And it comes back and finds 1 amp. So what I like about this is if you go back and change the value of one of the parameters, like we change k to 10, it right away resolves, and you see now that the current it finds is 0.835. Okay, so that's how you do it in MathCad. Now let's look at MATLAB. So I have MATLAB open here. Let me pause for a second and clean this up. Okay, so I've cleaned this up, and what I'm showing is the command window in MATLAB. You can put all these commands in a script as well, and save it as an M file, but we're going to just do it at the command window. I have my command history up here so that I don't have to type since I'm in my tablet mode. So what you want to do is we're going to define our parameters, like the voltage source Vs. So you just type Vs equal to 10, Rs is equal to 10 or 5, and then K equal to 5. So we have those defined. And then what you want to do is you're going to use the command fzero, okay, find a 0. And first off, let me show you how you can use it. It's very simple. If you want to find like the 0 of the sine function around 3.1, you would just type in f0 of sine, and then you give it the starting point, and it's going to look for a 0 near there. Of course, it brings back pi. If you do it around 6.1, it's going to come back with 2 pi. Now, if you here we have our own function. Okay, so the syntax is a little bit strange, but I'll bring this up and show it to you. Nope, that's not the right one. I want to correct that. I got a sign error. It's a plus. Get rid of that wasn't right. Vs plus Rs. Okay. Okay. Yes, so here's the syntax. You call the function f0, and then you put in, you can type in your equation that you want to find, that you want to solve for. And in this case, it's going to zero this, right? It's going to find the root of this. This has multiple variables in it, and you have to use this syntax, which is really a handle for a function, but it uses the at symbol, and then you want to put I in there because I is what we're going to iterate on, and the beginning value is 1. Now let's start somewhere else besides 1, just to show that this can actually find it. So if we started at 2, okay, it finds it, and this is finding the solution that yeah, this is the 1 amp that is saved, that is shown right here. Okay, so it solves it that way. So the function you want in MATLAB is the f0 function. Okay, so I'll put this in here, and we can copy it and stick it over. There we go. Okay, so that's what you want to use for MATLAB. Okay, so we've talked about Excel, using MathCad, using MATLAB, and then lastly, let's look at how we would use SPICE simulation. So shrink this to the right size. So I'm going to use NGSpice, which is available online. There's a version that runs online. You can download it also. It's based off of Spice 3, and here we just enter the net list. And so I'm going to show you two different ways that you can describe this circuit. Let me pull this over to the side, and what we'll do is bring back up the circuit that we're solving right here. Okay, so here's the net list right here to describe our circuit, our three-element circuit. I've got VS1 going from node 1 to 0. Here I've labeled the nodes 1, for instance, and 10 volts. R1 going from node 1 to 2 is 5 ohms. And then for any Spice 3 derived product, you can use a B source. So where you wouldn't be able to use it is if you're doing PSpice, like Cadence or OrCAD PSpice. It's based on Spice 2, and they don't implement the B source. But if you're using something like LTSpice, it allows the B source. The B source is really nice. If you click here on the documentation, there it takes you to a documentation page, and I have brought up the documentation on the nonlinear dependent source, and it's referred to as a B source, and it can be both either a current source or a voltage source, and that's determined by whether you type, after you put the two nodes, positive and negative nodes, do you put I equals or V equals. Okay, so we have the choice of expressing current in terms of voltage or voltage in terms of current. So in this first case, what I've done is I've expressed current in terms of voltage, and what that means is that I could express, if I'm going to express current in terms of voltage, I would have the cube root of Vx over k. Alright, and that's what I have right here. Okay, so the current source points from 2 to 0, so that means it's a current source pointing down, and it puts out a current that is equal to the voltage across it. All right, the voltage between node 2 and 0, which is the voltage across that element, divided by 5 raised to the 1/3 power. Okay, now that seems less natural than to express it as just 5 times Ix cubed. But here's the catch: if you're going to express it that way, which is what I've done here in the second circuit, you have to ask for the current flowing through the B source, and you can't. Now I realize there was a simpler way to do this, but at any rate, in general, if you want to know the current through a branch, you put in an extra voltage source in that branch, and you give the voltage source a 0 voltage, so it doesn't disturb the original circuit, but it allows you to query for that current by asking Spice to give you the current through that voltage source. Spice only reports currents through voltage sources. Now, as I'm talking here, I realize that because this is a single loop circuit, I have a voltage source in Vs, and I could have, instead of saying 5 times I of VB2, the 0 volt source, I could have said 5 times minus I of Vs1, or Vs2 in this case, raised to the 3rd power. So the analysis we're doing is an operating point or bias analysis, so we just put .op. So when you run this, comes back with the results down below. It's reporting these 9 values. And so if we're looking for current, let's just look at the current for our 2 voltage sources, Vs2 and Vs1 right here. Alright, that's the last 2 entries. And we find that in both cases they are equal to -1 amp, which means we have actually -1 amps flowing into their positive terminal. In other words, there's an amp current flowing clockwise. So there's an example of how you can use Spice to solve a circuit that contains a nonlinear element. And using the B source is very powerful. You notice in the documentation you can write all kinds of things like, the B source puts out a voltage that's log times the cosine of the log of some voltage squared. You know, it can be quite a nonlinear expression. One caveat: if you are using LTSpice and you can use the B source, but be aware that when you want to specify something to the power, you can't use the little caret symbol, because that's used. They use that for exclusive OR operation, because it's also a digital simulator, mixed mode. So what you have to do is actually type in. You use. Go down here. So for if it's LTSpice, you want to use. If you're going to do I to the third, you would actually write. They have a function called PWR power I, 3, and that's how you would specify raising some variable. Of course, you wouldn't put I, but maybe I of VS1 or something. Okay, so I'll stop here and continue in another video where we will discuss. Go back up here. We will discuss some graphical method, the graphical method, iterative method, piecewise linear model, and small signal linearization.